Okay, everyone. So what we're going to do is in this video, we will talk about resolution. Okay. So I will introduce you to this concept of resolution. What does this mean in stereochemistry? Okay. Now, as far as we're concerned, chapter 5 is concerned, resolution refers to the separation of a mixture of enantiomers. In fact, two enantiomers. Okay, so this is when we have a mixture of two enantiomers. That means we have a chiral compound. We have one enantiomer, which is depending on the number of chiral centers in it. Let's just say it's a chiral compound with one chiral center in it. Then one of the enantiomers is going to be of the R configuration, and its mirror image, which will be non-superimposable on this molecule, would be of the S configuration. Okay, so those would be the two enantiomers that we're discussing here, that we're talking about here. So resolution refers to the separation of a mixture of two enantiomers. Now, why is this important? Okay, the problem is enantiomers recall what these are. Enantiomers are two molecules, stereoisomers specifically, which are related to each other as non-superimposable mirror images, right? These are non-superimposable mirror images of each other. So that means the only thing that's different about the two molecules is the three-dimensional arrangement. And what that means is enantiomers usually have identical not usually. Enantiomers have identical properties. Okay, so let me correct myself. Not usually. Their properties are identical, except for one, which we'll talk about in a follow-up video, okay, which is optical activity. So we'll talk about optical activity later, but except for that, every other property that you can think of regarding enantiomers, they have the same property. They have identical chemical and physical properties. So that means they would have identical melting points, they would have identical boiling points, solubility, any of those things that you can think about, those are going to be the same. Okay, so enantiomers have identical chemical and physical properties, except for optical activity. Okay, this is in a separate video or in a separate in a separate video. So we'll deal with that later. Okay, so they have identical chemical and physical properties, because again, resolution, when you think about it, this is the key here, is separation. So if you think about it, when we think about separation from a chemist standpoint, how do we separate molecules? Like if I had a mixture of two compounds and if I wanted to separate them out, how would I do it? What are some things that you can think of? Like, so something that you might have done in the lab, like 3140, 3150, depending on, 3140 for all of you guys, 3140, or maybe in Gen Chem, that is a possibility. But how do you separate compounds? One of the properties that might come to mind is distillation. You basically do a simple distillation or a fractional distillation, and that would allow you to separate out the two compounds. And so the property that we are basically that we are relying on, the chemical property that we're relying on, is the boiling points. So if two compounds have different boiling points, then we can basically separate them out by distilling them out, right? We can distill them and separate them out. Similarly, if they have, let's say, different melting points, then we can use other techniques to separate them out. Or if they have different solubilities, then we can probably recrystallize and preferentially recrystallize one and separate them out. So that would not happen for a mixture of enantiomers. Okay. In fact, there's something that I should have mentioned here. So a mixture of enantiomers equal parts of two enantiomers is called a racemic mixture. Okay, so it's called a racemic mixture. Okay, it's called a racemic mixture. So what we are talking about here is how do we separate these out? Like if we have a racemic mixture, which is a mixture of two enantiomers, how do we separate that out? Okay, that is what we're going to focus on. So enantiomers, they have a big problem. They have identical chemical and physical properties, so they're not easy to separate out. Now, the other kind of stereoisomers that we've seen are diastereomers. Okay, enantiomers and diastereomers. Now, diastereomers, they have different physical as well as chemical properties. Okay, these have different physical as well as chemical properties, because realize that these are not mirror images of each other. Okay, they are stereoisomers, but they are not mirror images of each other. And so that gives them differing physical and chemical properties. So if we have two diastereomers, they're going to have different melting points, they will have different boiling points and solubilities. Hopefully, you know, it would depend on the compound, but you know, there are properties that we can probably exploit to actually separate things out. And that is the key to this discussion that we're going to have about resolution. So now in the textbooks, this is section 5.10. Okay, so resolution is 5.10 in the textbook. That's the section that we're going to talk about. I'm not exactly talking about what's in the book, but I want to give you a big picture of what is the underlying principle here. Okay, what is it that we exploit when we're trying to separate a mixture of enantiomers? Okay, so we'll go into that discussion. So resolution. So resolution is again separation of two enantiomers. So what we're going to do is for this, okay, as we talk about this, just to get you thinking about this and just to like basically help you understand this principle, what we'll do is we'll choose a molecule. We'll choose like an example. Okay, so let's assume, okay, let's say there is a chiral molecule which is A. Okay, A is a chiral molecule. There is a, I think I can write better. Okay, let's say, to make it simple, let's say A is a chiral molecule. Okay, and its enantiomer is A star. So we're going to represent its enantiomer by A star. Or we can use A prime, because we use star for the chiral center. So maybe use A prime. So A prime is its enantiomer. So if A is of the R configuration, let's say if A is R configuration, then A prime is its enantiomer, so that is its non-superimposable mirror image. Then A star should be S. Does that make sense? Okay, because they're both enantiomers of each other. They're related to each other as non-superimposable mirror images. So if we arbitrarily assume that A is of the R configuration, then A prime should be of the opposite configuration. So that's S. Okay, so a racemic mixture would be AR along with A prime S. That is a racemic mixture. Okay, we have these two together. That's a racemic mixture. A and A prime, they're both together. So how do we separate these out? That is what we're going to talk about. Okay, how are we going to achieve separation between these two compounds? Now, since these are enantiomers, based on what we just discussed, they would have identical chemical and physical properties except for optical activity, which we haven't talked about. Okay, that's the only physical, that's the only property that's going to be different, and it's a physical property. Other than that, everything else should be identical about these molecules. So how are we going to separate these out? Okay, so that is what we're going to discuss. So let's say we take this mixture of, or we take this racemic mixture, which is AR plus A prime S, and we react this with another chiral molecule. Okay, react this with another chiral molecule, but it's a pure chiral molecule. That means it's only one enantiomer. And so let's assume that B is of the R configuration. So B is a pure enantiomer. Okay, that means it's only one kind. It's not a racemic mixture, it's just one enantiomer. So since these have identical chemical and physical properties, and we are reacting them with this other chiral compound, a pure enantiomer, this reaction should give us two compounds. It would give us AR reacted with BR, okay, where the R enantiomer of A reacts with B, and plus it's going to give us A prime S with BR, where the S enantiomer of A reacted with B. So we got those two. And now, again, please remember that A and A prime, they are enantiomers of each other. So we are using the notation prime just to say that it's an enantiomer of that molecule. Okay, so we took this racemic mixture. This is a racemic mixture. We took the racemic mixture, we reacted it with a pure enantiomer of another compound. Any reaction that these can do. And I think it's too early to talk about some of these reactions because some of these things that we do, except for an acid base that you're going to see in the textbook, most of these reactions are like in 3150. Okay, so we can do a reaction, and this would give us ARBr and A prime S BR. So if I were to ask you, how are these two compounds related to each other? If I look at these two, if you notice, there's AR BR and there's A prime S BR. What would be the relationship between these two compounds? If you notice, there's BR, that's common to both of them. And then there's AR and A prime S. So that means one of the chiral centers in both compounds is the same or is retained. The other chiral center is inverted. So that means these are both diastereomers now. Okay, these are diastereomers. Now remember, again, diastereomers have different physical properties. So they might have different boiling points, they might have different solubilities, they might have different melting points. Anything or maybe everything may be different about them. So that means what we can do is we can take this mixture of diastereomers and we can actually separate these out. So separate these so that we get AR, BR, and we're going to get A prime S, BR. So now we've separated the two diastereomers. We've got them separated now. Now, if we take this compound here, ARBR, and if we reverse the reaction, whatever the earlier reaction was here, if we do the reaction in the reverse, what we would get is we would get ARBR. So we're basically trying to break that bond. Initially, we formed a bond. Now we're trying to break a bond. So we'll get ARBR, AR plus BR. And we're going to get over here, when we do the reverse reaction, we're going to get A prime S plus BR. Okay. So we got ARBR, AR plus BR, and we got A prime S plus BR. Now, AR and BR are two different compounds. One is A, another one is B. There's no relationship between them, which means they would have different physical properties. So their boiling points, melting points, solubilities might be different. So that means we can now separate AR and BR out. Okay, so we're going to get a mixture, but now we can get these two separate. Okay, so we can separate this, and so we will get AR and BR separated. And we can do a similar thing with this mixture here. We can separate these out because they are not the same compound. So they will have different properties and we can separate those out. And so if you look at it, overall, what we've done here is we started with a racemic mixture, AR and A prime S, which were enantiomers of each other. They had similar chemical and physical properties. To separate them as AR and A prime S here, what we did is we converted that racemic mixture into a mixture of diastereomers. And we're basically exploiting this property that diastereomers can be separated from each other. So we basically then separated the diastereomers out, and then we reversed the reaction that we did initially. And by doing that, we are able to separate out AR from our A prime S. We've separated that out. So that is resolution, which is essentially the separation of a mixture of enantiomers. Now, I just walked you through the principle of how resolution is achieved. So there are various ways that you can do it. Sometimes you can do acid-base reactions and then just recrystallize. Sometimes you can do a column and then other reactions. So there are possibilities, several possibilities, but the underlying principle to all of them is the same. You start with a mixture of enantiomers, a racemic mixture which is hard to separate, convert that into a mixture of diastereomers. Diastereomers can be separated, and then you basically reverse whatever you did to separate out the enantiomers. Okay, so that is chemical. This is, in some sense, this is chemical resolution. You can do physical resolution. So let's say a column would be sort of a physical resolution in some sense. Now there are other advanced things that people do, but this is the basic principle of all of that. So that is the separation of a mixture of enantiomers.